Okay, our next section is 7.2, and it's called two variable linear systems. Two variable linear solutions. Oh, I'm sorry, systems. Two systems. There we go. All right, so in the last section, we were solving linear and nonlinear systems of equations. So in this section, we are sticking strictly to linear. So both of our equations, again, we're sticking just to two variables, so that means two equations. So both of them are going to be linear. They're going to be lines when we graph them, and we'll find a finite solution where the two meet. So let's start with this set of equations. Again, two equations, two variables. We should get be able to get a finite solution, a point where they meet. So if I were to use, what we're going to do in this section is use a new method, and we're going to call it elimination. We won't use elimination when we have non-linear. We're going to stick to linear for elimination. Now keep in mind, you can actually use substitution for the linear two variable systems as well. But this is just, I actually think this method's a little bit easier when it comes to solving systems. So the goal when you're doing elimination is to eliminate one pair of variables. And the way you do that is by finding additive inverses for the coefficient. Additive inverses for coefficient of one set, not both, one set of variables. So just a quick reminder, additive inverses means that you have the same number, opposite sign. So plus 1 and minus 1 are additive inverses. Plus 3 halves, negative 3 halves. You get the picture here. That's 3 halves. All right, so looking at the original set that we have, you notice that we actually do already have. So this is an easy one. Negative 3 and positive 3 are additive inverses. So when you're eliminating some books will actually call this the addition method. And the reason why is because you eliminate via addition. What we do is we take our two equations, add them together once we have our additive inverses. So 2x and 5x makes 7x. Negative 3y and positive 3y equals 0y. They cancel out, which is why this works. And 7 and 0 makes 7. So now we have one equation, one variable. Remember, that's where we can solve. Divide both sides by 7. X will give us 1. So in order to find your y, we do exactly like we did in 7.1 with substitution, and we plug into an original equation. Plug back in. It does not matter which equation we choose to plug in. Either one works. And in fact, both should give you the very same answer. So we'll plug into the first one. How about that? So that's going to give me negative 3y equals 5. And then y would be negative 5/3. While I don't normally check them in both of them, let's go ahead and check in the other one just to show that it will work. 5 times 1 plus 3y equals 0. So that means that 3y equals negative 5, and then y would be negative 5/3. So indeed, we got the same solution. So our solution set for these two systems, these two equations, which make up a system of equations, is x is 1 and y is negative 5/3. That means if I were graphing these two, that they would meet they would meet at this point. I was thinking when I graph them, it's going to be hard to tell what negative 5/3 is, but they will indeed meet. I'll graph one in a minute here when we have one that's not a fraction, so we can see it a little bit better. So my next example, I'm doing another one because this one actually requires an additional step. Before, we already had additive inverses, so this one was really easy. So what happens if you don't have additive inverses as the coefficients? Example 2. We've got 3x plus 4y equals 11 and x plus 2y equals 5. So again, I'm trying to find additive inverses for one set of my coefficients. Neither of them have it. This is a 3, this is a 1, this is a 4, this is a 2. Neither of them have additive inverses. So I must create the additive inverses. It does not matter which set you use, just like in the last section, it didn't matter which set you solved for. Sometimes, as you get to do these more and more, you're going to see which ones are a little easier. But I always go for the lowest hanging fruit, whichever one looks easiest. Oh, I keep hitting it with my arm. All right, so what I'm going to do is I'm just going to take this guy here, and I'm going to multiply him through by -3. I'm multiplying the entire equation by negative. I'm going to put a little x, we'll put a little asterisk, times -3. So that would give me -3x minus 6y equals -15. Remember, it's still the same equation as long as I multiply every single term by the same constant. It remains the same equation. So you notice why I did that? Here I have a -3 as the coefficient of x, and the coefficient of the other x was 3. I created additive inverses. So this was equation 2. So if I take equation 1 and write it down below it, 3x plus 4y equals 11. Now I can use the addition or a method, or the elimination method, and just add them together. Add them together. Notice how my x's cancel. And -6y and 4y make -2y. -15 and 11 make -4. Solving for y, I get +2. Same process as before. I'm going to plug into one of my equations to get my x. I'm going to plug in the second one because it looks a little easier. X plus 2, my y is now 2. That means that x would be 1. All right. Okay, so graphically speaking, if we were to graph these, if you have two lines, let's say one is here and one is here, the point at which they intersect is the point that we're looking for when we're talking about a solution. Well, we also know that we can have two lines that are parallel to each other, and we know that two parallel lines never ever touch. So in this case, we have one solution. Well, if we have two parallel lines that never touch, we have no solutions, because they're not ever going to have a point of intersection. And we could also have two lines. When I graph, it just so happens that they end up being directly on top of each other. Not bad. So what that means is basically one is just a scalar multiple of the other. They are, if you were to reduce it, they would reduce down to the very same line. But you may not see that at first when you're working them. So if they are on top of each other, they have infinitely many solutions. Infinitely many solutions. That means that the lines are identical. So that's graphically what that means. Pretty intuitive there. So what happens when what does that look like analytically? So let's try an example. Let's try one that has no solutions first. So let's say we had x plus 3y equals 5 and -2x minus 6y equals 1. So I'm going to use the elimination method. Pause if you want to try to figure it out yourself first. Otherwise, I'm going to keep going since it's a video. I'm going to multiply this guy here by +2 to create additive inverses in my x variables. So multiplying him by 2, I get 2x plus 6y equals 10. I don't have to do anything to the second equation. Please note that there's times that you do have to multiply both equations by a constant. So if I add them together, my x's cancel. And look what happened to my y's. Positive 6y and negative 6y cancel out. I get 0 on the left. On the right, I get 10 and 1 make 11. So because 0 does not equal 11, this is an example where we have no solutions. And graphically, what I just said to you was no solutions mean these lines are parallel. They must have the same slope but different y-intercepts. All right, so what happens when we have infinitely many solutions? Again, this is if you didn't notice that they're the very same line. So let's look at an example. One that may not be quite as intuitive. 0.25x minus 0.5y equals 1 is my first equation, and my second equation will be negative x plus 2y equals negative 4. Again, just pause this video if you want to try and work it yourself. Otherwise, I'm going to keep going. All right, so I don't want to deal with fractions. So I noticed that I have 0.25. If I multiply by 4, I'm going to get 1 whole, and that will give me an additive inverse with my x's. So I'm going to multiply this line here by 4. So I'll get x minus 0.5 times 4 is 2y, and then 1 times 4 is 4. So that's my first equation, multiplied through by 4. My second equation, I'm just going to keep as is. You may be able to see it already, but when I add these two together, I usually like to change colors here. When I add them together, my x's cancel, I get 0. My y's, negative 2y, positive 2y, those cancel as well, I get 0. On the right, I get 4 minus 4 is 0. 0 equals 0. This is a true statement, so for this reason, we are going to say we have infinitely, did I get it right? Okay, infinitely many solutions. So that's analytically what that would look like if we had no solutions and infinitely many solutions. All right, so let's try an example with an application. All right, we have a man and a boat. A man and a boat can row 8 miles downstream in 1 hour. Can row 8 miles downstream in 1 hour. He can also row 6 miles upstream in 3 hours. How fast can he row in still water? And what is the rate of the current? How fast can he row in still water with no current, basically? What is the rate of the current? All right, so we've got, in the very first one, we noticed that he can row 8 miles downstream. So we're going to create an equation here. It's really not as hard as you might think. So his rowing, we're going to call R. Oh, goodness, keep hitting my hand on it. So his rowing is R. The current, R, will be the rowing speed, row speed. And we'll say C will be the current speed, because those are the two forces that are working here. His ability to row, and the current either working with him or against him. So we know that his rowing plus the current will give us 8 miles per hour. So in this one, we know that distance equals rate times time. So his distance in this case is 6 miles. His rate is going to be, well, let's say his time first. His time is 3 hours. So we're going to say 3 for his time. His rate is going to be however fast he rows minus the current that is pushing back against him. So that's going to be our equation. I'm going to rewrite it this way so that in the opposite direction so that it matches up with this guy here. So this is our system of equations. So let's, again, pause the video if you want to solve it yourself. I'll keep going. So this bottom guy is 3r minus 3c equals 6. I need my top guy, the first equation, to have an additive inverse. I notice that my c's already have opposite signs. So if I multiply the first guy times 3, the first equation, I'll get 3r plus 3c equals 24. And then I'm going to add them together. That'll give me 6 r's, c's cancel, equals 30, and r will be 5, which makes that the speed of his ability to row. His rowing speed is 5 miles per hour. And the current, again, I just have to plug back in. Remember, it's a system of equations. Let's plug in the first one. It's easier. So that's 5 plus c equals 8, which makes c 3. The current is rowing at a rate of 3 miles